a little bit about sampling in terms of how do you actually program an MRI scanner, and hopefully that's what we'll cover today. So just to remind everyone, in terms of K-space, the main thing we've talked about so far is that the signal we receive in MR at every point in time is essentially just the Fourier transform of our object evaluated at some place in K-space. Okay, so as time is going on, we are measuring different points in K-space. And where we are in K-space is determined solely by the gradient waveforms. And in particular, it's the integral of the gradients. Okay, and so essentially, the whole design of MR is how do you design the gradients. So we're going to start off with what's sort of the most popular pulse sequence, the most popular way of moving through K-space, and that's called the spin warp pulse sequence. And one of the key elements of this is simply these two pairs of gradient waveforms. Okay, so let's take a look at that. Let's see what's happening for the GX gradient first. Okay, so it starts off with a negative lobe. Okay, so that's going to move me out in KX from the center to a negative spot out here. Okay, so that's what that KX does. Okay, and then I start reversing the gradient, and so at this point in time, the integral is 0. So that means I've moved back to the center of K-space over here. Okay, and then I keep going, and so I keep going out here into K-space. All right, so it just moves me back and forth across K-space in the KX direction. Okay, so that's one element. The other element is, so this is what's called the readout gradient. And this is what's basically reading as we're going along in this direction here. So this way in K-space, we are essentially reading out the data. Okay, so that's why it's called the readout gradient. This gradient here is called the phase encode gradient. All right, and what it does is it simply, as I'm moving out here, so this gradient here is moving me over here in this direction here. This gradient here is moving me in the KY direction. So what happens is instead of just moving out horizontally, I'm moving out diagonally. Okay? So I move out to this point here in K-space. And then at this time here, I turn off the GY gradient. So I don't move any more in KY. And so simply the path is simply I'm just moving across here in K-space. Okay? So I'm doing flat lines in K-space along the KX axis. And so you can sort of get the sense that if for example, if I were to double the size of this gradient, then I would move out to a place that's twice as far down in the KY, and then I would come across like that. Okay? So that's all we're doing. We're going to just basically be changing the size of this gradient on every shot, and that's going to move us to a different starting location, and then we just zoom across K-space. All right? So that's the basic idea behind spin warp. So this is what the spin warp pulse sequence looks like. So these RF pulses here, we haven't really talked about them, but these are basically what we use to tip the spins and get the spins aligned. So we're starting off at every point we apply the RF, we'll assume we're at the center of K-space. Okay? So for now, just assume that those red points, those red RF pulses, are basically resetting the magnetization, so we're at the center of K-space. So in a later lecture, we'll talk about what's actually going on, but for now, just assume we're at the center of K-space. And so let's take a look at, for example, this first. So we basically, let's look at this thing here. So this is going to move us out to some place. So let's say it moves us out from here to here, okay? And then we zoom across like that. All right, and then we wait some amount of time, and then we come along with the next gradient here, and this is going to, it looks like it's about half the amplitude, so it's going to move us here and then across. Okay, actually, sorry, it's probably hard to see that. Let's use another color there. Let's use green. Okay, can everyone see that? Okay, and then here, on this last one here, let's use magenta here. We don't have any gradient here, okay, on the GY. So we're just going to stay along the KY axis, move this way, and then move along like that. Okay, so those, as we're doing that, and then the idea is, as we're moving along these parts of the gradient, we're actually collecting the data, okay? So we're only collecting the data as we're moving from here to here. So this initial part, we're not looking at the data, all right? Okay, so that's what sort of the spin warp pulse sequence looks like. So one way we can draw it is we can draw it as a function of time, and we can show that the gradients are changing in amplitude in terms of the phase encode gradients changing in amplitude, but the readout gradient is repeated every time. So that's the characteristic of the spin warp pulse sequence. So now what we can do is we can sort of, in terms of if we have a lot of phase encodes, then what we might want to do is represent it with just different colors or different, showing sort of how we might vary that phase encode gradient. So we already covered this one here, so that gave us this line. This gave us this line. When we don't do any phase encode, we get this line. And now we can think about what happens. Now if we apply this gradient here, a positive gradient, now we're going to move up in k-space first, so along this line here, and then we're going to traverse this way. Okay, so that's this line here. And then this magenta gradient here, this is double the amplitude here of the first one, so it's going to move us twice as far out in ky, and therefore we're going to move all the way from here, from the center out to here, and then we're going to cross over and go there in k-space. Okay? So that's basically the spin warp pulse sequence. We're just covering k-space in horizontal lines along the kx axis. All right? So let's just do an example of an object. So this might be, for example, we're assuming our object here is a two-dimensional rect function. So we know the Fourier transform is going to be a two-dimensional sinc function, okay? Where this is kx and this is ky, okay? So what we do in MR is we're essentially reading the data line by line. So the idea will be we'll be reading across lines like this, okay? We're going to acquire line by line the data in k-space, okay? So the first time we come through, we might expect to see something like that. When we do this middle line here, we should expect to see a pretty big signal coming through. And then when we move out to this line here, then we're back to a sort of small line. Okay? So we're going to do an example where we sort of simulate what might happen if our object is that. So let me pull up the PowerPoint. Unfortunately, I think this might screw up the recording, but let's just see how it works. Okay, so how do I launch the slideshow? So this is going to be an animation where this is the object here, and you're going to see along this axis, you're going to see different lines. We're going to be filling in k-space, and then here you're going to see the movie here, where you're going to see each line represented by itself. Okay. So you can sort of see there's not much happening initially. And so you're really just seeing, it's really probably hard for you to see, but there's a very faint dots appearing there where there's little peaks. You see it getting a little brighter. A little brighter. And there's sort of the main peak there. And we kept going like that. Okay, so that's how we're filling in k-space for a test object. Okay, so that was the example we did. Now, spin warp is just one way of filling in k-space. There's lots of different ways. So, for example, spin warp is what's called a sort of a Cartesian way of going through k-space. So that's nice because it's sort of easy to do the transform afterwards. There are other ways. For example, you could go through K-space using a spiral sequence. This is what's known as a square spiral, and we'll do an exercise on that later. You could do radially, so you could go out and do this. So what does the radial coverage of K-space remind you of? CT, right? So you can make MR look like CT by just doing radial acquisitions. Okay, and then you could apply a filtered back projection if you wanted to. Okay, and then you could also do what's called zigzag, or as most popularly used, it's called EPI, or echoplanar imaging. Okay, and so we'll talk about that a little more in terms of how it's applied, but for today, we're just going to look at the pulse sequence a little bit because it's related to one of the homeworks that will be that's coming out today. So this is basically where you want to just go through K-space very, very quickly. Okay, you don't want to go line by line by line. And so what it looks like here is you start off with a on the phase encode. It's still called phase encode. So you start with a phase encode that's going to move you way down here. Okay? And you're also going to probably start off with a frequency encode that moves you this way. So you're going to start off at some location here. So from the center of K-space, you're going to come all the way down to here. Okay? And then at that point, you're going to zoom across K-space this way. And then after you've done that, you apply one of these little blips here. Okay, that little blip moves you there. And then you reverse the gradient here, and so that makes you go the other way. All right? And then after you've gotten to the end of that, you apply another little blip here. That moves you up, and then you come across like that. So you can figure out these ways of just moving through K-space. All right? So this is what's called, at the top, single-shot echoplanar imaging. And it's sort of used everywhere for what's called functional MRI, which we'll talk about in a later lecture. So let's look at this movie here. I think I have it here. Let's see if it works. Nope, that's not going to be good. Let's try it here. Okay, let's see if the audio works on this. Let me get the audio working here. Okay, what we're going to do is I'm just going to put my iPad on, crank it full blast. You guys are even listening. Ready? So that's basically the magnet making that sound, okay? So MRI is a very noisy, and that's one of the problems with it. It's a fairly noisy modality. So typically you want to reduce the noise, but in this case they're actually trying to make use of it. just heard was you heard the swallow, and then you heard drrrr. And so what you're seeing is basically, this is, for example, showing you the readout gradient going back and forth. And that's what you're hearing. As the gradients are switching back and forth, you have currents going through the gradient coils, and those currents in the presence of a large magnetic field vibrate, okay? And that vibration acts as a big speaker. And these gradients typically pulsate at the audio frequency, and this is why you can hear them, okay? So in this case, you can sort of see the readout gradients there, and these are the little phase encode blips that move it up in k-space. Okay? So what they're trying to do here is they're trying to basically acquire the data and then have the magnet tell the subject to swallow. They're looking at kids with feeding tubes here, and so they were trying to look at what the brain is of these kids who have feeding tubes in them. All right? So that's showing you that, one sort of gradient trajectory. Why don't we do one more, which is it's totally irrelevant, but sort of fun. Let's see. What is it called? Smoke on the water, I guess. That sort of gives it away. Yeah, so this was a sort of fun thing that someone did a long time ago. So what you're hearing there is that's called the pre-scan. The scanner is figuring out, it's calibrating itself. And then you're also hearing that's also calibrating. Okay, so that's at a channel called MRI Nerd. So there's lots of other fun things at that channel. So you can, there's a YouTube link to that, so you can have fun with that. Okay, any questions up to now in terms of k-space? Okay, so what we want to talk about next is sampling in k-space. And so you already sort of looked at this a little bit in one of your homework assignments. The basic idea is that if I have, this is my object, and this is its Fourier transform, then what I'd like to do in MR is I'd like to acquire this data and then do the inverse transform and come up with an image of my object. All right, so that's ideally what I like to do. But I don't necessarily have the time to acquire all the data I'd like, and so one thing we want to look at is how much data do I actually need to acquire? Okay, because it's a time, we're acquiring data as a function of time, the more data we acquire, the more time it's going to take. So this was an example here, shown here on the lower corner here, where we essentially zeroed out every other line, every other column. And so basically, if you look here, along some of these columns here, we've just zeroed out the data. Okay, we basically said, let's just skip every line of data and see what we get. And when we do the inverse Fourier transform, we get this image here, where the object is replicated. Okay. Similarly, we can play this trick here, where we skip every other line going in this direction. And now we see that the image has the replication going in the y direction. We could also skip every other line both this way and this way. So we're really trying to sort of save on how much data we're acquiring. And now we get lots of replication. Okay? So this is what's called aliasing. In general, we want to avoid doing that. We want to sort of take it right to the limit. But we would like to, for example, you don't really necessarily, this is not really the image you would want if someone was trying to diagnose something in your brain. Okay, you'd like not to have aliasing. So in general, we want to avoid aliasing. let's sort of get a sense of why aliasing occurs from sort of the spin perspective. And so once again, what we have here in the first row here is we have the spins all aligned. And then we assume that they're in the presence of gradient, and then we're looking at what happens as they evolve as a function of time. Okay? And so we notice that, for example, this spins here, they start processing faster. And these spins here process slower. Okay? And we talked about how basically as the spins evolve, we're going through different parts of K-space. All right? So now let me ask you a question. Let's take a look at the spins in column 1. Let's call this column 1. And let's call this column 2. Okay? What do you notice about the spins in column 1 and 2? Anything? It's not a trick question, so they're just doing the same dance, right? Okay. So from the point of view of when we sum up all the spins, when we integrate, we can't differentiate them. Okay? So in that sense, spin 1 looks exactly like spin 2. Okay? Because it's doing exactly the same thing over time, and so basically we don't know where it came from. Okay? Similarly, what can you say about spins in column 3 and column 4? They're also doing the same thing, right? So this is a case where spins are going to alias. So these spins here, when we do the reconstruction, are going to be mapped to lie right on top of those spins there. Okay? So what could you do to make the spins in column 1 and column 2 look different? What would you have to do to make them look? Yeah, go ahead.
Just sample like different, like slightly off.
Okay, sure. So what do you mean by slightly off?
So if that coordinate is like x equals 2, then we do it at like x equals 1.9.
Okay, so basically this is the x-axis here, right? So that's the x-axis, and then this is the time axis here, right? Okay. So we do want to sample differently, but which axis would it be along? Probably time. Yeah. Is that what you're going to say?
No, I was going to say if you actually lower your resolution, you just desync it, but then still get what you're looking for.
Can you say that again?
If you actually widen out your resolution, like make it worse, you'd still actually get a better picture because it wouldn't be synchronized.
Okay. So one thing is you could have less resolution, so that might be one option. But let's say you want to keep the resolution the same. So one idea is these two guys are doing, from the way column 1 and column 2 look like they're doing the same dance, but in fact column 1 is going clockwise, is going faster, and column 2 is going slower, right? So what happens is we just haven't sampled them finely enough in time. Okay, so it's sort of like sometimes you watch a tire. If you watch some old movies like With a Wagon Wheel, any old Western movies, and then sometimes it looks like the wheel is going backwards because of the synchronization of the movie camera sampling with the speed of the wheel, okay? So that's called aliasing. So essentially something going one way can look like it's going the other way if you don't sample it at the right rate, right? So what it means is we actually have to sample more finely in time. So now let's look at column 1 and column 2. So now do the spins look different? Yeah, so you can tell that, now you can tell that this spin here is going clockwise, right? And this spin here is obviously going counterclockwise. Okay, which you couldn't tell from before, right? Because we were sampling too coarsely. Okay? So the idea is between here and here, that gap we've reduced. Okay? And so let's say this was some kx, this was at kx equals 0, and this was some delta kx. So essentially we're trying to make this, the kx that we've gone in that time, we want to reduce that delta kx. Okay? So that's what we're going to go after. There's another view of aliasing that we can think about where you can think, it's the same idea, but basically the idea is, let's say I was at a kx of, so this is my field of view. Okay, so the field of view, FOV stands for field of view, and it's essentially the size of the object that you care about. So let's say my field of view spanned this range here, okay? But let's say I came in with a phasor pattern that had this as one period. So that's one period. Okay. So you can sort of see that this spin has the same orientation as that spin. Okay. So when we do the transform, this phasor pattern will multiply this object here. This spin will multiply that object. When they get all summed up, we can't really tell that they come in sort of in the same way. They multiply by a spin in the same direction. So this point will get aliased to that point there. All right. Whereas if we had something that had a longer period, so this has a much longer period. Okay. So now this spin here looks different from this spin here. And so when they come in to the multiplication and the summation, they'll look different. All right. So what we're getting at is we need to sort of figure out that it turns out that the solution we're going to be after is that given some FOV, I can say that my delta kx is going to be just 1 over the field of view. Okay, and so that's going to be the design equation we come up with. So we're going to go through a little bit of sort of background math, but the nice thing is after we've gone through it, the actual design parameters you come up with are super simple. Okay, they're just taking one parameter and inverting it and to get another parameter. So let's sort of take a little bit review and talk about sampling and review some of what you need to know about sampling. So sampling is essentially taking a continuous object and converting into discrete samples. In this case, a sampling interval is delta x. It could be anything. It could be, for example, delta kx or delta y or whatever you want to make it. But in this case, we're just saying it's delta x. And so these are samples. G of n is a sample of my object at the nth interval of delta x. Okay? So that's all it is. To denote what we mean by sampling mathematically, we come up with this thing which we call the comb function. Okay? There's other names for it, but in this class we'll just call it the comb function. And this is also known as an impulse train or a bed of nails or the Shaw function. It is essentially just delta functions at every integer, 1, 2, 3, and so on and so forth. So it's just a train of delta functions. That's all it is. It's also useful to have scaled comb functions. Okay, so comb of x over delta x just makes it such that the spacing is delta x. All right, because in general we want to be able to vary the spacing that we sample at. Now, when we do this, there are sort of these leading factors that you sort of have to carry around. For this course, don't worry about them. Just really focus on what's the spacing in either space or Fourier domain. All right? The most important thing, though, is to remember what the Fourier transform of a comb is. So the nice thing is a comb just goes to a comb. Okay, so what could be simpler, right? So basically, if you see a comb function, comb of x, you know that its Fourier transform is just comb of kx, right? So that's all you need to remember about the comb function, all right? Now, what that means is, though, if I take a comb function that's scaled by delta x, I'm going to get a comb function that's spaced with 1 over delta x. And so that's an example of the scaling function theorem. And so here's the main picture you need to remember. If I have something that's spaced delta x in one domain, and I take the Fourier transform of that comb, the spacing is going to be 1 over delta x in the other domain. Okay? So you can just sort of think of this as sort of a form of the scaling theorem, where as I squeeze it in one domain, it's got to get wider in the other domain. All right? So that's going to be the most important thing to keep in mind as we go through the math. So now let's sort of apply that to MR. And we have, in MR, we're sampling in Fourier space. All right? So let's assume that our object was this rect function here. So we know its Fourier transform is just going to be a sinc function shown here on the right. And now the idea is we're going to take this sinc function here, and down below, we're showing samples of the sinc function. And the question is, depending on how I sample the sinc function, I take these samples and I do the inverse Fourier transform on them. And the question is, what is my object? Okay? So ideally, we'd like to get back the rect function, but the only way we can do that is if we sample like infinitely fine, right? The sinc function. So we want to just sort of get away with, what's the minimum we can get away with in terms of getting a sort of a relatively good representation of rect function. All right? Okay, so for the Fourier sampling, we're going to use a comb function, and the spacing is going to be delta kx, or delta ky. So it's essentially delta k is now our sampling. And so let's look at how that looks. So this is my Fourier transform of my object. So this is the sinc function. I multiply it by a comb function that has a spacing of delta kx. So that's my sampling. And these are my samples here. Okay? So the question is, what is the inverse Fourier transform of this guy? And the way we do that is, remember, this is a multiplication in the Fourier domain, right? So this is a multiplication. So what do we do in the image domain? If we multiply in one domain, what do we do in the other domain? We just convolve, right? So this is convolve. So that means that in the object domain, we just take our object and we convolve it with the train of Dirac delta functions with spacing 1 over delta kx. And so this is just going to lead replicas of my function with spacing 1 over delta kx. Okay? So essentially, sampling in one domain leads to replicas in the other domains, and so the whole name of the game is don't have those replicas overlap, right? If I can keep these replicas sufficiently spaced apart, then I can always cut out the part I want, and then I should be able to recover my original signal, right? Once they start overlapping, then I have aliasing, and that's what you saw. You saw those images overlapping. Okay? So that's simply, MR is simply showing you that that's what happens in reality, that if you don't sample finely enough, you have your images overlap. And that's just shown here. So if you assume your object has some width, field of view, some size, then the requirement is pretty simple. You just want these replicas not to overlap. Okay? So this spacing, 1 over delta kx, just has to be greater than the field of view. All right? Because if it's less than the field of view, then those things will overlap. So typically what we say is, for the design, it's sufficient just to go to the limit. So we'll just say that the design requirement is just make delta kx equal to 1 over the field of view. All right? So when you do your problems, you can just set it equal to 1 over the field of view. So this is what happens when you don't satisfy Nyquist. So you end up with this overlap here. Okay? In this case, delta kx wasn't small enough. Okay? And so that's what we want to try to avoid. Here's an example where we really don't meet Nyquist. So here, I guess the field of view here is, we're right at Nyquist. So here's a case where it sort of falls apart even when we're right at Nyquist, where the field of view is 1, delta kx is 1, but if we sample this sinc function, we only sample this thing, and everything else is zeros. And so we end up with this thing on the right, and then when we do the inverse transform, this is like a delta function, so it just transforms to 1. So these replicas, they're right next to each other so that the overall function at the end is just 1. Okay? So that's sort of like showing what happens right at the limit. But in this case, well, for our purposes, in general, for a field of view, the object is going to be somewhere in the field of view. So even if they touch, it's okay because we're okay allowing them those boundaries to touch. Okay, so that's, even though this is right at the limit, that's okay for us for our design problems. We'll let delta kx equal 1 over the field of view. So since we're dealing with images, we have to deal with 2D comb functions. Okay, and so this is just the same. Where this unscaled, it has a spacing of 1 in both the x direction and the y direction. And we can also have scaled comb functions such that it's either delta x or delta y. Okay? Or in our case, we'll use delta kx and delta ky. And so this is sort of what we're going to do. We're going to take our object here, g of kx, ky, and we're just going to multiply it by this comb function that has spacing of delta kx and delta ky. And that's all we're going to do. All right? So this is what the picture looks like. So we've sort of gone through the math, so the rest of the lecture is just really focusing on how do we apply it and what's the big picture. So this is my object here. And this is its Fourier transform, okay, which is a 2D sinc function. So this is sampling here. Okay, so this is multiplication by this grid here, where this has spacing of delta k. Okay, that means I'm going to convolve here, and so the sample pattern then just looks like this. It's a sampled sinc function. Then in the image domain, I simply take my object here, convolve it with this comb function that now has 1 over delta k spacing. So that now just leads to replicas of my original image. And as long as they don't overlap, then I'm okay. All right? So that's all we're talking about in terms of we acquire the data here in this domain, here in the Fourier domain. And as long as we meet that requirement, then we know we'll be okay in the image domain. Right? So this is summing it up. This is just the Nyquist condition. So essentially, we just need to meet these conditions here. And as I said before, for your problems, it's sufficient just to say delta kx equals 1 over f of e in the x direction, and delta ky equals 1 over f of e in the y direction. So sometimes f of e in the x and y will be the same, but in general, you can have rectangular f of e's. For example, if you're imaging the spine, you might have a very long in one direction, but narrow in the other direction. All right? So you do need to pay attention to both the x and y field of views. Okay, so let's do a really simple in-class exercise. So this is your object here, g of xy, cosine 2 pi 3x plus 2y, rect of x over 3, rect of y over 4. So the question is, what is the k-space sampling needed to avoid aliasing? Assume that the spatial units are in centimeters. Okay, so I'm going to open up the poll, and then we'll take a look at that. Okay, great. So let's take a look at this. So let's sketch our object first here. So along x and y. So how wide is this object in the x dimension? 3, right? So it goes from minus 1.5 to 1.5. And how wide is it in the y direction? 4, right? So it goes from 2 to minus 2. And so that's the shape. And inside, it's doing something like that, right? We don't really care right now, okay? So the first part is just meant to confuse you, okay? We'll talk about that later, but for this, so the point is the first part doesn't actually matter yet, okay? So what we know is, so what is the field of view in the x direction here? It's just 3, right? Because the object is limited to that, right? And what's the field of view in the y direction? 4, right? So we simply take our design rule. Delta kx equals 1 over f of e of x equals 1/3. Delta ky equals 1 over f of e of y equals 1/4. Okay, so that's all we were looking for in that problem. All right, any questions? Okay, great. The next aspect we have to look at is something called windowing. So we've already talked about how finely we're going to sample. The next question we have to answer is how far out in k-space are we going to go? We don't want to go out to plus or minus infinity because that'll take forever. So we need to actually cut and make some limit. So how do we define windowing, or how do we define that in k-space? So this is what you could acquire if you had all the time in the world, right? This is the ideal Fourier transform. And this is what we call our windowing function, or a window. And that's going to limit how much you can acquire. So what we actually acquire is not g, but g of w, or g sub w. Okay? So for example, if the Fourier transform was like this, we might just say we're only going to acquire it within some window. Okay? So this whole thing is g, and we're just going to acquire the part this part is G sub W. The part that's inside the window is G sub W. All right? And that's obviously going to have some effect on our image because we're not acquiring all the data. And the question is, how far out do we need to go in k-space? So now we look and see this is a multiplication here, right? This is a multiply. So I've multiplied in Fourier domain. So therefore, I must convolve in the image domain. So I'm going to have my original object. Okay. And I'm going to convolve it with the inverse Fourier transform of my window. Okay. So that's all we're going to do. So essentially, we're going to take our object and we're going to convolve it with something. And we want to look at what's the effect of involving my object with this something to be determined. All right? So let's look at the big picture here. So the big picture is I have my object here, and I have my Fourier transform of my object. Oh, sorry, that's not wrong. That's incorrect. The Fourier transform of my object is over here. Okay, so this is a rect function, and this is going to be a sinc function. All right? And so if I had all the time in the world, maybe I could sample this whole thing, but I don't. I'm going to take this G, and I don't know why I used M here, but let's use W. So this is my window. After I multiply G by my window, I'm left with this G sub W. Okay, so you can sort of see it's the original data, but I've just chopped out. I've only kept the part in the middle. And we know from our previous examples that's going to lead to some blurring, right? We remember when we kept only the center K space, the image became blurry. We lost the details. So what does that look like in image space? Well, this window here is just a rect function, right? And therefore, its inverse transform is just going to be a sinc function. Okay. So what it means is I'm going to take my object and convolve it with my sinc function. And it ends up, that process lends to this sort of blurry image. So imagine everywhere I had a really smooth dot, I'm replacing it with this wavy thing. Okay. And if I did that process over and over again, I'm going to end up with this blurred image. And so that's what we're looking at. So the question is, how much blurring can I allow? Okay. So this is just describing what we just did, which is basically saying that if my windowing function is a rect, then I'm going to have sinc functions in its inverse transform. So then my object just really gets convolved. So this is convolved with these sinc functions. Okay? So that's all we're doing. We're just taking my object and convolving it with sinc functions. So one useful thing is to say, what's the effective width of a sinc function? Okay? So, for example, in this case, the sinc function I care about is sinc WKXX. Okay? Because I had my windowing function was rect of KX over WKX. Right? So this was the width in Fourier space of my window. And therefore, by scaling theorem, it goes to a sinc function, but now this WKX comes here, okay, by the scaling theorem. So the question is, what does this look like? Well, this is something, this sinc WKXX has zeros and multiples of 1 over WKX, all right? And it turns out that the effective width of this function turns out to be really simple. So the effective width of this function, sort of how fat that function is, just 1 over WKX. Okay? So that means that if I go farther and farther out into K-space, my effective width is 1 over WKX, so it shrinks and shrinks and shrinks, which makes sense. The more data I acquire, the width of that sinc function should get narrower and narrower and narrow. In the limit, it becomes a delta function, right, as I go out into infinity. All right, so that's good. So that makes sense. And it's also nice that we just have to remember just 1 over WKX, right? I'm going to skip over that for today. So let's take a look at an example of that. So it turns out that WKX, in this case, we have two delta functions here, delta of x and delta x minus 1. And so these are two delta functions spaced 1 apart. Okay, so the spacing of my object is just something at 0 and something at 1. And we're looking at what happens when we convolve these with sinc functions. Okay, so if my effective width is, if my wkx is equal to 1, then my effective width is just 1 over wkx, and that just equals 1. And so you see when we do that, the effective width is 1. And so now when I look at these two sinc functions, so this is the first sinc function convolved with a sinc, the first delta function convolved with a sinc. This is the second one. When they add them together, I just have one peak. So at that point, they've merged together. So it's just one dot. So there's two dots became one dot. Okay? Whereas if I looked over here, this over on the right, this effective width is 1/2. So it's got half the effective width. So now when we look at those two sinc functions, you can definitely tell the blue one from the green one. And when I add the two together, I definitely can tell the two dots. Okay? So the limit we're going to pick is what the resolution limit is when you have two dots that you just, at the limit where they just merge together, that's sort of the design rule we're going to come up with. Okay? So now we're going to put everything together, and we've got my object is here. Here is its Fourier transform. In this case, I sample it, okay, and here I window it. Okay, so here I'm going to replicate. Okay, so this leads to all these different replicas here. And then I'm going to convolve it with this sinc function here. So each of those replicas gets blurred out. And you can sort of, it's hard to tell, but if you look closely, each of these is sort of a blurred version of the original. Okay, so there's two things going on. I'm replicating things, I'm also blurring them. And we sort of want to take it to the limit where we make it so the replicas don't overlap and also the blurring is acceptable. All right. So that's just shown here where we've, this is the replication and this is the blurring, okay? And so that's the convolution with the comb gives us the replication, the convolution with the sinc gives us the blurring, all right? And so at the end of the day, once we've gone through all the theory, the nice thing is that the design rules you have to use are actually fairly straightforward. So basically, if you're given the FOV, then use it for delta K is equal to 1 over the FOV. Okay. The other thing you're typically be given is the resolution. So someone will say, I want to be able to resolve things at like 1 centimeter or 1 millimeter. You take that and you say, okay, well, given that, I know that the amount I have to go out in K space is just 1 over delta X. Okay, so that turns out to be the design rules that we have. So let's do an example of that. So here's the object now where you actually have to think about what this cosine thing is doing. So I want you guys to sort of think about, so you're the client, right? You're basically have this object and you're going to someone who's going to design an MRI pulse sequence for you, and you're saying, okay, I'd like you to image this object with a certain resolution. So that's the first question that you have to answer. And then the designer's, the MRI person's job is then to take your resolution requirements and figure out what the width in K space is. Okay, so in this case, you're playing both roles. First, you want to think about what would the resolution of this object, what would be a good resolution for this object? And then secondly, given that resolution, what should I do in K space? All right, so that's your job. Okay, let's take a look at this. So remember, let's draw our object again. So we have X and Y, and we know it's got this FOV here, or it's 3 in this domain and 4 in that domain, okay? And from before, what we said was the previous parameters we tried was delta X equals 1/3 and delta KY equals 1/4, okay? So in the KX domain, we know that the sampling interval is 1/3 here and 1/4 in that direction. Okay, and now we want to ask how far out do we go in k-space? Okay, so it's probably not going to be the case that that far out is 1/3 and 1/4. Okay, because the sampling is already 1/3 and 1/4. Okay, so that's sort of a sanity check. That it's probably going to be much greater than 1/3 and 1/4 because you're going to need to sample out into k-space. Okay, so that's one thing to look at. The next thing to look at is we want to now think about what the cosine is doing, right? Because if this was just a uniform object, then obviously there's no detail on it, and so we don't really need to go that far out in k-space. So in that case, maybe that 1/3 and 1/4 is sufficient, okay? But in reality, we have a cosine 2 pi 3x plus 2y. So let's look at both in the kx and the ky direction. So in the kx direction, we have something like cosine 2 pi 3x, okay? So this is something with a frequency of kx equals 3, right? So the spatial frequency is 3 because we have it's in the form 2 pi kxx. And therefore, this is something that will, let me erase this for now. So we have a cosine in the x direction that has a period of 1/3, right? So if I have something with a period of 1/3, so it's going up and down, what would be a reasonable interval to sample that at? 1/6, right? Every other, so you get the peaks. So probably what you want to do is make delta x equal 1/6, okay? And then you can say, oh, well, in that case, so that's the first part, and then wkx is just equal to 1 over delta x equals 6, right? So that's just this width here. This is now 6, okay? But the question didn't ask for wkx, it asked for kx max. Okay, so it's the maximum kx you go out to. So what would that be? 6 over 2, right? So then kx max would just be 6 over 2 equals 3. Okay, so that's how you would do that problem there. And similarly for the y direction, kx equals 2. So the period is 1/2. So we probably want to make delta y equal half of that, so 1/4. So wky is equal to 4, and therefore ky max equals 2. Okay? So, so then basically now we've said that this width is 4, and the farthest I go out is 2. Okay? So that's basically the design that you have to do in all of medical imaging, but in particular we're doing it for MR imaging, which is how far do you go out, how much do you sample, how finely do you sample, and how much do you sample. Okay? All right. Any questions before we move on? Okay. Yes?
So I noticed that in the x direction, you are going to have more samples.
Yes.
In the y direction?
Yeah.
The max ky is smaller, and also delta ky is larger. Right?
Yeah. Yeah.
So won't that look like an object?
Oh, okay. So what the question is, in this direction, the width is 6, right? So since the sampling is 1/3, I'm going to have about 18 samples, right? And then here, in the y direction, the width is 4, so 4 divided by 1/4 is 16 samples in that way. Okay? So I do have more samples along one than the other, which is fine. In general, I've gathered the information I needed, basic fine-tuned to what was in my object, okay? Because my resolution was different in one direction than the other direction, and the FOV was different. So it's okay to actually have different numbers of k-space, okay? All right, any other questions? Okay, we're going to do one, okay, so this is what this actually looks like. This is from a GE scanner, and so typically people will specify, so you sort of see here, you zoom on it. You can see here they've specified the field of view, okay? And instead of resolution, typically we sort of specify a matrix size here. And so in this case, the delta x would just be the field of view divided by the matrix size, which is 256, which is basically how many pixels you want to have in that direction. Okay, so that's how it's done on one scanner. On another scanner, this is sort of like a Siemens scanner, but still you see the field of view here, and also you see this sort of the matrix size here. Okay, so if you're not given the resolution, but you're told how many, it's sort of like when you buy your computer or your TV, right? It's like 4,000 by 2,000 or something, right? So you know the size of your TV, and then the voxel size or the resolution is just simply that width divided by how many voxels or pixels you have. So it's the same thing with MR. The user will specify the field of view. It will specify the matrix size, and then behind the scenes, the code is doing exactly the same calculations that we just did. All right. So we're just going to go through one example of that together. So just to remind you, what you're typically given is the user will specify the field of view in both the x and the y direction. They'll specify some resolution, either directly or by saying what the matrix size is. And then from there, your job is to figure out the delta k's and the width in k-space. All right. Now we're going to translate that into what it means for the gradients. So we're going to apply it to the spin warp pulse sequence. So we're going to actually design actual MR pulse sequence now and go through the design of that. So once again, we said that each time we go through one of these readouts with a different phase encode value, we are acquiring a line in k-space. Okay, and we're just going through k-space, acquiring line by line by line. So now the question is, how long do we make these lines, and how far apart do we make these lines? So that's the only design question. So the first question is sampling in kx. Okay, so what does that mean? Well, for each one of these lines, you can imagine as I'm going along the line, I'm actually going to be measuring the MR signal a long time. Okay? So there is some intrinsic delta kx that I'm sampling along that kx line. Okay? The way that sampling is done in practice is with the electronics. So this is the demodulation here. We've talked about that before. And then this is the sampling part, okay? So in every MR system, there's something called an analog to digital converter, which both samples and also quantizes. We're not going to talk about the details, but essentially it's taking samples in time, all right? As we march along k-space, it's just looking at it at different points in time. So that's what we have here. So as we're moving along k-space, along the kx axis here, we're just sampling in time such that we have some delta kx. Okay? And since that traversal happens as a function of time, so over here on the left, I'm showing this gradient. And so essentially, if I sample with some delta t, and typically you'll be given the sampling rate or you can specify it, then the question is, how much of delta k, well, x, do I travel in some time delta t? Okay, so that's the question. So if I'm looking every delta t, I'm just seeing how far do I travel every delta t in k-space. So the answer is simply, what's the incremental area of that gradient that I travel in delta t? Okay, so the answer is just, it's gamma over 2 pi, the magnitude of the gradient, gxr, times delta t. Okay, so that's my delta kx here. And then if I know the FOV, I can figure out what delta kx is. So then I know what delta kx is, and then I can solve for either gxr or delta t. I'm usually given one or the other, or there might be constraints, but I certainly have enough information to solve for that. Okay, so let's look at an example of that. So here's a real-life example. Let's say the field of view is 25.6 centimeters, which is a good field of view for like a human head. Okay. If you need bigger field of view for a human head, then that is probably very unusual, okay? And let's say that the resolution is delta x equals 0.1 centimeters in both x and y directions. So what's the matrix size here? So how many voxels do I have in each direction? Right, 256 by 256. So this is going to be a 256 by by 256 image that I want to create. Okay? So let's say that we're given that the delta t is equal to 32 microseconds. Okay? So what we say is, well, my delta kx is just 1 over the field of view. So it's 1 over 25.6. Okay? And that equals gamma over 2 pi times gxr times delta t. Okay? So I'm given delta t. I know this, so I just solve for gxr. And if I do that, I end up with 0.2867 Gauss per centimeters. So I've basically solved for the amplitude of that gradient. Okay, so that's one calculation that if you actually look at an MRI scanner, the code that runs it, you'll see code almost exactly like that. All right. Any questions? Okay. The next question is the resolution in the x direction. So remember, the resolution depends on how far out do I go in from one end of k-space to another end of k-space. Okay? So basically, to go from this side of kx to this side of kx, that's done by this gradient, this gradient, right? That's the gradient that does it, right? It moves me from one side to the other. So how far I move is simply the area of this gradient, right? Okay? So I already know what gxr is. I already solved for gxr, right, in my previous thing. So now I just want to solve for what's the width of this gradient going to be. Okay? So I know, so the question is, the area of this gradient is also is going to be wkx. Okay? Because that's how far I want to move, which is equal to 1 over delta x is the resolution. Okay, which I'm given. So in this case, it's 1 over 0.1. And that area is simply going to be gamma over 2 pi gxr times tau. Okay? So I'm given, I know this, I solved for this before, so now I just want to solve for tau. Okay, in this case, it's called tau sub x, let's say. All right, so once again, I'm just solving for the area, and I can do that, and let's see how that turns out. So this turns out to be 8.192 milliseconds. Okay? And so that's by solving sort of that area. Now the question is, how could I have come up with this answer a little more easily? And it's shown here. It's basically, I know I need 256 samples, right? So I was already given that. So this is 256, and I already know that this is 32 microseconds. So it turns out that I could have also just solved it just by looking at it that way. Okay? So any questions on that? So basically now we've figured out how big this gradient should be. We figured out how long we should play it out for, and then we're basically done with the readout gradient. Okay? All right. So now let's look at sampling in KY. Sampling in KY is how far apart these lines are spaced, this spacing here. All right? And so it's basically the difference between, for example, this gradient moves me out some distance, and then the next gradient moves me out less distance. It's basically the difference between those points that it moved me out to. So it's really sort of this incremental area here, okay? Let's see. Let's call it incremental area. All right? And so typically, we want to solve for either this incremental area or the width of it. And you'll typically be given one parameter or the other. But in either case, the delta ky, that incremental area is simply this area here. Okay? So that's just gamma over 2 pi times the sort of this incremental amplitude times the width. And this is just equal to 1 over the field of view in y. All right? So typically I'll be given this, and I will solve for either this or this. All right? And that's the design problem. So let's take a look at that. time. Okay, so here's an example. Here I'm given tau sub y equals 4.096 in milliseconds. Okay, so what I would say is gamma over 2 pi times 4.096 times my incremental amplitude is equal to 1 over the field of view in the y direction, which is 1 over 256, 25.6. Okay? So then I can just solve for GYI, and I end up with that there. Okay? And the final thing that I have to ask myself is, how far out do I go in, what is the width in k-space I go out in ky? Okay? So that's just given by delta y equals 1 over delta ky. And a couple ways you can think about it is we can define what's the maximum gradient that you're going to apply in the y direction. So this is the maximum gradient, and let's say we're symmetrical, so negative it would be minus GYP, okay? So I know that if I apply the maximum one, it's going to move me out to this part in k-space, and then this guy will move me out to this part in k-space. So the span between these two guys is my delta ky, all right? So that's just going to be given that area, the incremental area, the difference in those areas is just gamma over 2 pi times 2 GYP times tau sub y, okay? And then that's just equal to 1 over, so this is delta ky, and that's equal to 1 over delta y. So I'm typically given the resolution. I think probably given this tau sub y, so I'll just solve for this gy sub p. So here's the example here where we are we're given the resolution 0.1 centimeter. We're also given this tau sub y, and so we just solve for this gy sub p, and we get 0.2868 Gauss per centimeter. And this just turns out to be 128 times the GYI. Okay, because we know we have to have 256 samples total. So I have 128 samples this way and 128 samples that way, and that's a nice sanity check. So when you're done with these problems, you can sort of say, does everything match up? All right. So that's sort of how. So what we've gone through now is how to design a spin warp pulse sequence, and the main thing is FOV determines delta K. And resolution determines WKX. And your job is to translate this into areas. Okay? That's all it is. It's just, if you want to break it down into the steps you'll have to take. Now, one morning is, we've done this for a spin warp pulse sequence. And so, in general, the steps we take will be, this general approach is always the same, but the actual calculations you do depend on what sequence you're doing. Okay? So what I'd like you guys to do is, just summarizes it, is for next class, I'd like you to think about this problem and submit your answers to this in the first few minutes of the next class. So we'll about the first 5 minutes of Wednesday's class for you to submit your answers to this. And this is now, you're designing a pulse sequence that does this trajectory for you with those design constraints. Okay? Question?
Can you upload them?
Yeah, this is in the slides that are posted. Yeah. So this is the thing you'll do. So you'll assume that gamma over 2 pi is 4,000 hertz per Gauss. This is the trajectory you want to take, and the assumption is that you start off at this point in k-space here, at the center, and then every delta t you move 1 hop. Okay? So the time interval between those dots is this delta t of 10 microseconds. So first delta t, you move 1, and then you move the next, and the next, the next, next, next. So the warning is you can't just apply the spin warp stuff to equations directly. You need to just think more about the basics of how do you move in k-space, and how do the areas do that, and how are the requirements of FOV and resolution tell you what you need to do in terms of, so for example, here, this is obviously my delta ky. There's going to be some delta kx, right? And then there's also, how far out I'm moving in k-space. Okay, so your job is to, given the k-space trajectory, design the gradients that will achieve this for you. All right, and so you can upload your answers to the 288 poll. We'll sort of open that up at the beginning of next lecture, and we'll talk about this at the beginning of next lecture. All right, any questions? Yes, in the back. Oh, yes, graded homework 5s are here. Homework 6, I guess, is turned in here. Homework 7 will be posted. Okay, so homework 6s are back there. Homework 7 will be posted later today. And because of the Thanksgiving holiday, it's not going to be due till next Wednesday. And we're going to have, because there's no TA office hours Thursday or Friday, we'll have TA office hours Monday and Tuesday for homework 7, and then additional TA office hours Thursday and Friday of next week for the last homework 8, which will be a short homework. Okay? And then also, just a reminder, final project proposals are due Wednesday at 10. We'll talk a little bit about the final project groups during Wednesday's lecture. Okay? Any other questions? Yes?
I understand we've been only doing this, assuming that there's no relaxation whatsoever.
Yes.
That graph and scan lines actually refer to the x-axis as you go along, and or would you have to compensate with these non-square wave pulses?
Where you are in k-space will still be determined by the gradients. It's just whether you have any signal there or not. It's the relaxation. Right. Yeah.
But they would relax and converge toward the axis, right?
The k-space trajectory itself, if it's just pure relaxation and there's no what's called off-resonance effects, then it would still just be, you can still think of it as you're still sampling k-space, but the signal is decaying. So you can sort of break it up into the sampling, what you're sampling, and then the trajectory you're taking. Yeah.